Hi everyone, my name is Caitlin Yang and I'll be walking you through tutorial 3, which will show you how to train a simple regression model. When we refer to training a machine learning model, this is the process where the model learns how to make accurate predictions based on data that it hasn't seen before. In other words, this means fitting a highly parameterized function to map inputs to outputs. Training helps the model learn the parameters that relate the input features to the output prediction. In this case, we'll be focusing on training a regression model, which is used when we want to predict continuous numerical values. This determines the relationship between the input and the output predictions, or the explanatory and response variables. First, let's take a look at a brief workflow for this process and introduce some important AMPL functions and classes. Using the previously curated SLC6A3 dataset from tutorial 1, we'll define some key parameters. Depending on whether we want to use previously split data or if we want to split the data and train the model in one step, we'll modify these parameters, split UUID and previously split. Elliot introduced the parser wrapper function in the previous tutorial, and we'll again use that to handle our parameters. Elliot also used a method in the model pipeline class to split the dataset. Now we'll use the method trainModel to fit a model to the train dataset. Then we'll use this getFileSystemPerf function to create a performance table and measure the accuracy of the models on validation and test sets by looking at the R-squared metric. We'll then sort that table to find the model with the best validation R-squared score and save that model and all of its parameters in a tarball. Now, to give a little more background information, this is the basic equation for a linear regression model, where y is the predicted output or dependent variable, such as pKi values, x sub k are the input features or independent variables, such as molecular descriptors, beta naught is the constant or intercept, and beta sub k are the coefficients that determine the relationship between each feature and the predicted value. Regression models are important because they allow us to predict a continuous outcome based on input data. This can be used to model a wide range of scenarios. For example, given inputs like the features of a house, such as its number of bedrooms, stories, and age, a model can generate a prediction on how much that house would cost. In cheminformatics, regression models are especially useful to make predictions, such as the properties of a drug. Properties like solubility, boiling point, or binding affinity to a target protein can be estimated based on a drug's molecular structure. These predictions can also be used to improve the design of new molecules with optimized properties like melting point or bioavailability. In another example, these features can also be correlated to biological activity, and the effect of a drug on patient recovery can be predicted based on medical features. Lastly, regression models can also be used to predict the toxicity of chemicals to living organisms or their impact on the environment, which is important to help assess the safety of new compounds. These models are important tools for making predictions and understanding relationships, and training is needed for the model to learn to make accurate predictions from data. In the case of AMPL, inputs on pharmacokinetic properties can be used to generate predictions on the effects of a drug. It's important to note that this linear model is a very simple example, and in practice, AMPL uses much more sophisticated models in the drug discovery process. In this specific example, our model will predict pKi values for inhibition of SLC6A3. Now let's take a look at how this is accomplished. We'll train a random forest model using the curated SLC6A3 dataset and split file from the previous two tutorials, as well as the RDKit features calculated by the AMPL pipeline. As Elliot explained in tutorial 2, three-way data splitting involves subsetting a dataset into training, validation, and test sets. Following this, since we'll be training the model using an existing file provided with AMPL that was split following the steps of tutorial 2, this file ID is specified by including split UUID as one of the model's parameters. Previously split is set to true to tell AMPL that we don't need to split the data again, since it's already been done. RDKit features will be used for this tutorial. RDKit is a collection of cheminformatics and machine learning software, and it includes many features, including molecular and substructure descriptors. However, it's important to note that AMPL provides an extensive featureization module that can generate many different molecular feature types, and it's not limited to RDKit features. Using RDKit, the raw data will be processed into a set of features or chemical and molecular descriptors that are more useful for training the model, resulting in a featureized dataset scaled by molecule size. This will be saved as a CSV file under the Scaled Descriptors folder. So let's run this first cell. After importing the required libraries, we define a few variables such as our dataset file and directory. Here, this split UUID is saved under dataset. Some parameters that we're specifying include the prediction type, which again is regression since we're training a regression model to predict PKI values. The descriptor type refers to the feature type, and again we're using our dkit. Since we're using a previously split model, previously split is set to true, and the split UUID is specified. The model type is RF, which refers to the random forest algorithm. This is an ensemble learning method that can be used for both classification and regression tasks, and it involves training multiple decision trees on different parts of the same training set. It's a commonly used machine learning algorithm because it can capture complex relationships between features and the target variable. Once we've defined the parameters, we can run the train model method. This method will complete the training itself, and now this will give us a trained model that can make predictions on new unseen chemical data. In this second example, let's say that we don't have a pre-split dataset, in which case AMPL will perform the splitting automatically and train the model in one step. Unlike the previous case, the previously split parameter will be set to false and the split UUID parameter will be omitted. Instead, the splitter parameter will be included and the split file will be written as a CSV file directly under the dataset folder rather than the scale descriptor subfolder as in the previous example. This approach is convenient because you don't need to manually split the data yourself. However, avoid using the one-step process if you intend to compare the performance of multiple models trained with different parameters on the same dataset. This is because each model will have different splits, so this adds an additional variable in determining the performance of each model. Since you want to make sure that the differences in model performance are due to parameter settings, not due to the random variations between splits, then in order to compare two models, they need to be on the same split, or the test splits need to be the same. Now let's run this cell and set our parameters. Again, previously split is set to false because AMPL is handling the splitting internally. The splitter parameter is set to scaffold. Scaffold splitting splits molecules based on their structural scaffolds so that molecules with a similar core structure are grouped together. The split valid frac and split test frac parameters are both set to 0.15, meaning that 15% of the dataset will be used as the validation set, which is used to evaluate the performance of the model and tune hyperparameters, and 15% will also be used as the test set, which is used to evaluate the final performance of the trained model on data that it hasn't seen before. Again, we're using our dkit descriptors and a random forest model. And just like before, the train model method will be used to perform the training. Now that this training is complete, let's evaluate model performance by seeing how accurate its predictions are on validation and test sets. Again, the validation set is used to fine-tune the model's parameters, and the test set evaluates the final performance of the model. AMPL has many different metrics to assess model performance, like mean absolute error, root mean squared error, and R-squared. For these tutorials, we'll use the R-squared metric to compare our models. The R-squared value, or the coefficient of determination, determines a model's goodness of fit for the data by measuring the proportion of variance in the dependent variable, in this case PKI values for inhibition of SLC6A3, the value that the model predicts, that can be explained by the independent variables, in this case molecular features of the compounds. R-squared values generally range from 0 to 1, where 1 means that the model perfectly predicts the output, so a higher R-squared value will indicate better performance. It's also possible for R-squared values to be negative in cases when the model does not fit the trend of the data and fits the data very poorly. Now let's compare the models. First, we'll import compare models from the AMPL framework, and this function will obtain the performance results of all the models stored in this directory that we stored both models in earlier. The pred type equals regression argument specifies that we're evaluating regression models. Information such as the model UUID, model path, AMPL version, model type, features, splitter, and the results for different performance metrics will be stored in the perf.df data frame. Now let's save the data frame and then take a look at 5 of the most useful columns within it. This shows us the model and split IDs for both models, as well as the best R-squared scores achieved on the training, validation, and test dataset. The training R-squared quantifies how well the model fits the data it was trained on. The validation score helps evaluate the model's performance on data that it hasn't seen during training, and the test score gives the final evaluation of how the model performs on data it has never encountered before in training or validation. Comparing these values, we can see that the R-squared is fairly similar for both models, but that this second model performed better on the test set, whereas the first model performed better on the training and validation set. Also, notice that in both cases, R-squared values are higher for the training set than the validation and test sets. This is important to pay attention to, as we want to avoid overfitting the model, which might be indicated by the model performing very well on training data, but not as well on data that it hasn't seen before. Alright, and finally, let's find the top performing model based on the R-squared scores. We define the top model as the one with the best validation R-squared score, which is found by sorting the perf.df data frame in descending order based on this column. This reveals that the best model is the first one that we saw in the data frame. Now, when we take a look at this best model, we can see its important information, such as the model ID, the path to the saved model, the model type, features, and splitter, which we've defined earlier. We can also see more performance scores, such as the R-squared on the training, validation, and test data, the root mean squared error on the training and validation data, and the mean absolute error on the training and validation data. Now, if we want to run predictions with this best model later, we need to save its path. Top.model.model_path will show the path to the tarball where the model is saved. And now that we have the best machine learning model for predicting the inhibition of SLC6A3, we'll be able to make and evaluate predictions using it, which will be covered in tutorial 4. Thank you so much for watching.